Hello followers, welcome to the second episode of Dive into C++. Today we're gonna dive a little deeper into some features I talked about in the last video, and then we're gonna expand our Arkanoid game by dealing with Frametime and FPS issues. So let's begin by diving deeper into the constexpr keyword. Last time I showed you that constexpr is a new keyword that was introduced in C++ 11 that allows you to define compile time expressions and constants. Now there is a very important way you can use constexpr, which is defining functions that will be computed at compile time. So as you can see here, the constexpr keyword can also be applied to functions. A big restriction that will be lifted in C++ 14, is that constexpr functions can only be composed of a return statement. So if you have a constexpr function, it must be a single return statement. Also, constexpr functions will be resolved at compile time if the arguments you pass in are constant expressions, otherwise they might get resolved at runtime. And you can call only constexpr functions inside of other constexpr functions. So you have these big restrictions, but you are allowed to do compile time computation, and that's very useful when dealing with things like arrays. Let's see some examples. So I've created here a function called getSum that returns a constexpr int and takes 3 arguments. And it basically just returns the sum of these 3 arguments. In my main, I can call getSum 1, 2, 3 plus 5, and it is guaranteed by the standard that this will be resolved at compile time, because 1, 2, and 3 plus 5 are constant expressions. So the compiler is able to perform this computation at compile time. But if I load an input from scene and I pass that into my getSum, I'm guaranteed that the function will not be run at compile time, because it's impossible for the compiler to know what the input is before runtime. So this function will get called and will give the correct result, but it will be called and computed at a runtime. Also, since constexpr is often resolved at compile time, we can use it to declare arrays, for example. Saying something like int array of getSum 10, 10 is the same as saying int array of 20. So you can use constexpr function to aid you in doing expensive computations for I don't know, Fibonacci and other numeric series. So you can use constexpr as a way of dealing with compile time expressions such as array initialization and make it a little easier. Then we have another feature that I briefly talked about in the last video, which is uniform initialization syntax. And these are some of my thoughts and why I prefer uniform initialization syntax to the classic traditional syntax. So I created a little class here called example. It has a constructor which takes an int and prints out constructor, and an operator equals that takes an int as well and prints out operator equals. So as you can see, the signature of the constructor and the operator is basically the same, because they both take int parameter, but they do completely different things. One prints out constructor and one prints out operator equals. So you could say something like example1 equals 10. This might look deceiving, because it looks like you are assigning 10 to a new variable example1, but in reality you're calling the constructor as you are defining example1. So even if there is an equals here, you're actually calling this function, the constructor. So when you do something like example1 equals 10, constructor will be printed out, not operator equals. And if later, instead of defining a new variable, you call equals on a previously defined example, in this case example1, you will obviously get operator equals, because we are not constructing anything here, we are just assigning. So my issue with this kind of output is that we're using the same symbol, the equal symbol, for construction and for assignment, and it may not be confusing for experts and people who dealt with C++ for a lot of time, but for beginners I think it's really, I don't know, annoying, because you can get confused, and also it's really unelegant in my opinion. So we could instead use uniform initialization syntax, which allows us to be very explicit about what we are doing. So if we call, if we define a new variable called example2 of type example and use the uniform initialization syntax with the curly braces, we will be sure that we're calling the constructor. There is no confusion here, there is no equals operator. So defining it like this is, in my opinion, a good practice, because when you see this line, you are sure you're calling the constructor here. Also, you can't obviously type anything like this, because you cannot assign with curly braces. So you are sure that when you see curly braces, you are constructing, and when you see the equal sign, you are assigning. It's elegant and really straightforward, in my opinion, and I use uniform initialization syntax this way in all of my code. It also has some benefits. It avoids the most vexing parse, which is basically saying something like int variable. This seems like a variable definition, but in reality it is a function definition. Obviously we'll not compile it in here, but if it was in outside main, it will be a prototype for a int function that takes no argument. Instead, if you say int variable curly braces, the compiler knows you're trying to define a variable and initialize it with nothing, and so it avoids the most vexing parse. It's also cohesive, because it uses the same syntax as aggregate initialization, and aggregate initialization is when you have a simple class like struct point int x int y. If I'm not mistaken, you could do point x equals 1 2 in before C++11. Now you can do point x 1, 2. And what I mean by cohesive is that you can use the same syntax as aggregate initialization, array initialization, and initializer lists as you do for constructing normal variables. So it's very elegant, in my opinion. It also, obviously, as I talked about in the last video, prevents data loss implicit conversions. So if you have a float and you try to create a new int and constructing it via that float, it will throw a warning or sometimes an error. So it's good to know that you're losing data in a conversion. Another example is having a struct, I call it vector2, like the SFML one, which is simply an aggregate of 2 floats. And we can avoid repeating the keyword vector2, sorry, the type name vector2 when returning, for example, from a function by using the uniform initialization syntax. As you can see here, we have to say return vector2 of 5 of 5, while here you can just say return and construct a new instance of vector2 of 5 of 5. The two functions are equivalent, but the second one is shorter and it avoids repetition. Also, there is an important note to take care of. In some occasions, when we use auto, we should avoid using the curly braces, because when using curly braces with auto, the compiler always deduces the type to be initializer list. So if you say auto x equals 5, it's fine. Auto will be deduced as an int. If you say auto x parenthesis 5 close parenthesis, it's fine, because x will be deduced as an int. But if you say auto x curly brace 5 curly brace, it is misleading, because it looks it looks like a construction, so an int, but in reality you're constructing an initializer list. And basically the rule is that when you use auto, you cannot use curly braces unless you want it to be an initializer list. So let's now move on the Arkanoid game. Last time we had a playable game, but it had a big issue, and that is it was frame rate dependent. So if, for example, on a slow computer the game would have less FPS, the game would run faster or have less precision. So that's something we really want to avoid. And today we are gonna see how we can fix that problem and also other minor issues. Let's begin with the first code segment. And actually now we're gonna get into a very important thing in C++, which is const-correctness. And basically it is a way of marking functions to specify that they are not gonna modify the class they're in. So if we have some getter functions, and by getter I mean some functions that just return a value or a simple calculation, like our shortcut functions to get the various position of the ball and the bricks, they should be marked as const, because they are not modified. They are not modifying any member of the color. As you can see here, they're just doing simple calculations, and it also expresses explicitly the intent that the function isn't going to modify anything. And most importantly, it allows us to call these functions on const references and const pointers of the class. So if, for example, we have a const references to ref2ball to any ball, for example, if we hadn't the const specifier here, we wouldn't be able to call ref2ball.x, because as a const reference we are only allowed to call const members on ref2ball. Also, if you mark something const and then you later on add something here that modifies a member of the class, you will get a compile time error, because if you mark this const, the compiler knows that it cannot modify any member of the class, and it will not compile. So it's very important to be explicit with our const correctness in our C++ programs. Also, there is a new C++11 keyword that is called noexcept, and allows the programmer to help the compiler optimize the code by marking certain functions that we are sure never show an exception. So C++ has this mechanic that allows us to catch errors, that's called exceptions. And basically, if something goes wrong, for example when reading a file from the hard drive, we can just throw an exception, and something later in the code we deal with this exception by catching it. And also, if we show an exception in a library, the user can catch it in its own code. So it's a very flexible way of dealing with errors. Unfortunately, before C++11, we had a flawed way of marking functions as non-throwing exceptions. We would say, for example, const throw like this. And while this allowed the compiler to do some optimizations, if an exception was actually going to be thrown here, because the programmer didn't know, for example, that getPosition could throw an exception, then the program would become corrupt, and that's very bad, because anything could happen when your program is corrupt, and finding this kind of bugs is really difficult and time consuming. Instead, C++11 gives us a much more powerful and useful keyword, which is noexcept. And by marking functions as noexcept, we allow the compiler to do some optimizations. And in the rare case that we mistakenly mark a function noexcept and it throws an exception, the program will terminate. That means we will not have runtime corruption, and we will avoid undefined behavior, which is very important. So my suggestion is to use noexcept whenever possible, because one, it could make your program slightly faster, and two, it expresses the intent of having a function that do not throw exceptions. I've also created a new class, which is rectangle, and it is a way to encapsulate and abstract the common members of both the paddle and the bricks, since they are both rectangles. We can avoid copy-pasting all of this stuff in both the paddle and the brick by creating a class called rectangle, and we can use inheritance, static inheritance in this case, because we are not using any virtual method, so that paddle will be derived from rectangle and brick will be derived from rectangle. There is no runtime overhead at all, because when we use static inheritance, it is practically the same as taking all of this and copy-pasting it in here and in here. So it is a very easy way of abstracting some shared properties between classes and to make our code shorter and easier to maintain. And another feature I didn't talk about in the last video is member initialization directly in the class. You couldn't write this in C++ 03 because it was a compile time error. You had to write it like this. First, you had to declare the destroyed member, and then in the constructor, you would say destroyed false, like this, to initialize the variable with the value false. But now you can avoid this code repetition by simply initializing the variable inside the class in C++11. It's a very handy shortcut, and it also helps you remember if it helps you see that you have declared a variable and initialized it, because it's easy to miss an initialization in the constructor. And I think there is another part in this code segment which is very, very important, and this is event polling, and this is a feature I forgot to talk about in the previous video. It is an SFML feature. It is required on some operating system to call window.pollEvent during the game loop, otherwise the window may freeze. And it also allows us to react to common events, such as dealing with the window being closed, dragged, resized, etc. And it also allows us to get input directly from the OS, and immensely simplifies text entering. For example, when you have an X score table and you want the user to enter its name, there is a simple text entered event that you can use to get the right letters. So how does it work? We create a little buffer, we can call it, that is simply an event instance, and in a while loop we constantly poll the current event inside our event buffer, and then we work with the event buffer. So if, for example, the current event has type event closed, we know the user has pressed the X button on the window, and so we will close the window and break out of the game loop. So it is very useful to deal with common events, but if you don't want to do, if you don't care about closing the window or dragging or resizing, you can simply avoid typing anything in here. But the important thing is having this while loop, because it allows the events to be processed and avoid freezing the window on some operating systems. So it's always a good idea to put the poll event loop inside your game loop. Okay, let's compile the game. You shouldn't notice any change, because we only changed the code a little bit. The behavior is exactly the same as before. Let's move on to the second segment. Okay, now we're gonna deal with the very important issue of frame time and FPS. So we'll begin by introducing a new C++11 keyword, which is using, and it's used as a type def replacement, and it's much more powerful and much more elegant. And we can use it to define aliases for types. For example, I defined an alias for float, which is Frametime. So whenever I say Frametime, it's the same as saying float. You could also say using integer equals int, and it is an alias for int, and it's basically the same as saying type def int integer, but it has a very easier syntax, and it is less confusing. Also, it is more powerful than type def because it allows you to do templates. For example, you could have template type name t using my vector equals vector2 of t, and then you could say my vector float, and it will be the same as vector2 float. And again, you can still use it with templates. You can say using my vector float equals vector2 float. So when you say my vector float is the same as saying my vector2 of float. So it's a very useful tool to make your code shorter, more elegant, and more expressive, as we're using the type Frametime to deal with FPS calculations. And since we want those to be very explicit, we're gonna avoid using float because it's too generic and it may get confusing. So let's skip to the game loop. Okay, to the main function, I mean. So as I was saying, our code has a critical issue. It is frame rate dependent. So if we set the frame rate to 60, the code will behave the same way, unless we have a slow computer that cannot handle 60 frames per second. But it's not a good solution at all. Instead, we should pass the last frame time, and by frame time I mean the last time the frame took to both update and draw in our update methods, so that we can scale our movements and actions with the frame time, achieving frame rate independent behavior. What I mean is that if we have float velocity equals 100, and if our last frame took 1 to be computed, we will simply move the ball by velocity per last frame time, which is equals to 100. Now, if the last frame took twice as long to compute, to avoid changing the behavior, we need to move the ball twice as fast. So it will be 200. If our frame took half the time to compute, for example, the 0.5, we would need to move the ball half as fast, so by 50. So we're basically scaling our movements, our actions, our velocities by the frame time to have a frame rate independent behavior. This is a solution, but it's a naive solution. I will talk about a much better solution in the next code segment, but for educational purposes and to follow a gradually more difficult process, we will see how to implement this solution. So let's begin by commenting out the frame rate limit, because we don't need that anymore. And now we're gonna use a new C++11 amazing library, which is Chrono, that you can use by including the Chrono header. And this library basically allows us to precisely deal with time and the system clock, so that we can accurately get time points, durations, and periods, and basically do calculations on those. So we will first start our time interval at the beginning of the game loop by creating a variable of automatic type by getting the current time from the Chrono high resolution clock, and we basically say chrono : high resolution clock : now, and this is a global function that will return the current time as calculated by the high resolution clock. And we will store the current time into time point 1. So we do our stuff here, we update, draw, etc. And after we've done all of that, we must get to the second time interval that will be slightly higher than the first one because we did all of this stuff, which is not free. So we do the same, auto time point 2, chrono : high resolution clock : now, and we get the current time after the updates and the draws. So we now have a time period that is basically time point 1, time point 2. We can get we can say the magnitude of the period, the duration of the period, by basically subtracting time point 1 from time point 2, and this is what we are doing in elapsed time with the auto deduce type. We basically just subtract the end time point from the start time point. Sorry, we subtract the start time point from the end time point, and we get an std : chrono : duration object, which represents a time period between two time point objects. So we'll also need to get the frame time in milliseconds, and we're gonna print it as the Windows title for now to see what the frame time is. And we will use the very safe and useful duration cast chrono function, which allows us to specify how we want to cast a duration and get the correct result. In the end, we need to convert the duration to a float, so we'll use the .count member function. So let's analyze this code. We are defining a variable of type Frametime, which is an alias for float, and we're initializing it by casting elapsed time to a duration of type float and the magnitude of milli, which means we are using a ratio of 1:1000, and that equals to milliseconds. And after we casted the elapsed time, we will count, and that basically just converts the duration to a floating point variable so that we can store it inside ft. Then we also want to calculate the FPS, and we can do that by getting the seconds from the ft. And if we divide milliseconds by 1000, we obviously get the seconds. And we can get the FPS by doing this calculation, which is basically 1 divided by the seconds it took to execute a frame. Now we are gonna print out our values in the Windows title. We use the window.setTitle as FML function, and we will use the new std toString function, which was introduced in C++11 and allows us to cast, to convert a numeric value to an std string, which is very useful in a string concatenation situation like this one. So we say ft plus ft converted to string plus a tab, and fps plus fps converted to string. We will see our current value in the window.setTitle, and also the game should run insanely fast, and we will fix this in the next code segment. So let's compile and run it, and let's see what happens. Okay, as you can see here, the game is going extremely fast, and in our window we have our ft, which is our frame time in milliseconds, that cycles between 0 and 3, and our FPS, which cycles between 200 and 2000. So now that we have calculated the frame time as the FPS, we need to scale movements and actions to avoid behavior changing based on the frame rate. So to do that, we need to make our velocity constants a lot smaller to deal with the new frame time values. So basically it was 6 before, now it's 0.6, and also the ball was 8 and now it's 0.8. And now we need to scale movements and actions by the frame time, and to do so we must pass the lastest frame time value as a parameter in all of the update methods of our game. So in the previous code segment we didn't have a parameter here. Now we have a frame time MFT parameter that we'll be using to scale our velocity. So it's very simple. Instead of moving the shape by the velocity, we simply move the shape by the velocity multiplied by the frame time, so that we are scaling our velocity based upon the latest frame time. So if it took longer to execute, the shape will move more. If it took less time to execute, the shape will move less, so that the behavior stays consistent. We do the same into the paddle. As you can see, velocity multiplied by MFT. And the only change here is storing the last frame time value into a variable that I call last FT. And I also added some set frame time limit commented out instructions here, so that we can test the game at different frame rates easily. And inside the game loop we simply call update via last FT, so that we pass the last calculated frame time inside the update methods as a parameter. And last FT is obviously assigned after we calculate FT from the game loop. So let's test it out. Okay, we are at 240 FPS and the game goes reasonably well. And it's smooth, and it isn't faster than it should be. Let's try changing our frame rate to 60, and let's see what happens. Okay, the game is now running at 60 FPS, but we don't notice that because the behavior looks exactly the same as before. Now let's see what happens when we decrease the frame time even more. Let's set the limit at 15. Okay, now we see that we have a big problem. Even if the movements and the actions are scaled correctly and the game doesn't actually run faster or slower than before, the precision of the movements has been obviously altered, and sometimes the ball moves more than a single block, and it can completely skip a collision check. As you can see here, it goes straight through the blocks because the frame rate is too low and the magnitude of the ball movement is too high, and it skips some bricks. This is very bad, as it can completely change the game's behavior depending on the user's machine. So, as you may have noticed, the game seems to behave the same way at any frame rate. But at very low frame rates, something horrible can occur. Velocity can be so high that certain collision checks get skipped, because objects completely jump over other objects. So if, for example, our bar velocity constant is 0.8 f, and if our FPS is 15, our frame time will be equal to 66. And that means that we'll be multiplying 0.8 f by 66, which is 52.8 f. This is almost 3 times bigger than the height of our bricks. So it is almost guaranteed that the ball will skip collision with some bricks, and this will completely ruin our game. Let's see how we can prevent this from happening and still prevent the game's behavior from changing based on the frame time in the in the next code segment. Alright, now we are going even deeper into the FPS frame time issue, and we'll see a seemingly complex way of solving the problem, but it's actually not very difficult, and it works quite well. It has some drawbacks, but it is very used today, even in AAA games, and it's a reasonably good solution. So, to prevent behavior and precision from changing with the frame rate, we need to use a constant MFT value, so that when we go and call update, we will be sure the shape will be moved by the same velocity every time. So this MFT must be constant. But if the MFT is constant, we will obviously see difference in at higher and lower frame rates. So to avoid that, we need to divide our game time in different slices. I've drawn a simple diagram here with text. As you can see, we have one slice here, another slice here, another slice here, another slice here. And we can get the position of the slice by having a slice variable, and this is slice multiplied by 1, by 2, by 3, by 4, and so on. And every frame we will call update with the constant MFT n times, where n is the number of slices we pass through with our last frame time. For example, if our last frame time starts here and ends here, it goes through 2 time slices. So we will call update 2 times in a single frame. This might seem counterintuitive, but it is a very effective way of preventing precision changes and allowing the game to run the same at any frame rate. So basically, if a computer is very slow, our frame time might be very long, and we'll have to update the game 3 times in a single frame. If the computer is fast, our frame time may be very short, and we may have to update a single time in a single frame. Basically, the time we need to update is the times we need to update our game in a single frame are the slices we go through with our last frame time. So, no matter how big or small the last frame time was, we will always call update in fixed intervals, which are our slices. If the game goes extremely fast, we will completely skip the updating fast during center frames. Otherwise, if it goes extremely slow, we will probably need to update multiple times during a single frame. This method allows fine control, our movement precision, and guarantees the same behavior with any FPS. So, let's see how we should implement it. Before doing anything, we must define some constants. One constant will be the step for the frame time, which is basically MFT. So if our step is 1.f, we will pass the step as our MFT, so we can be sure that our MFT will always be 1.f. And another is the slice constant, which will be the size of a single slice. In this case, it's 1.f. All of the code for the game objects has been unchanged. The only difference is in the game loop. So we need to define another variable, which is current slice, and it will accumulate the current frame time, so that if our frame time, if we accumulate our frame time and then our current slice is greater or equal than the ft slice constant, we will update once. Otherwise, if it's greater or equal than the slice constant multiplied by n times, where n is bigger than 1, we'll need to update multiple times in a frame. So let's say, for example, that our last ft was 5. During the game loop, we basically add 5 to current slice, and then we need to repeat our updates for 5 times, because current slice is 5. Basically, this means that if we pass through 5 slices with our last frame time, we need to update the game 5 times in a single frame. Also, you may notice that if the frame time was smaller than the slice, it will take 2 frames to get the slice bigger than 1, and in some frames the game will not be updated at all. So that was just an example. Let's see how it is implemented in the real game loop. Before doing that, we must say that dealing with the events and the input should be done every frame to ensure maximum responsiveness. So we shouldn't do this along with the updaters. We should deal with events and the input every frame, regardless of having passed a slice or not. Then we begin our update phase. We start by accumulating the last frame time into current slice by using the compound operator plus equals. And now we will use a for loop to subtract the current slice. To subtract the ft slice from the current slice, while the current slice is bigger than ft slice. So basically, if current slice is greater or equal than ft slice, which is our constant, we update our game logic and decrease current slice by ft slice until current slice becomes less than ft slice. In layman's terms, basically, if current slice is 3 times as big as the ft slice constants, we need to update our game logic 3 times. And if current slice is less than 1 time as big as ft slice, we will not need to update anything, and we will wait until during the next frames current slice will become as big as ft slice. So basically this is a way to update the game multiple times or no times inside a single frame. So instead of this for loop, we put out all of our update calls, and instead of passing last ft here, we pass our constant ft step, which is 1.f if you remember. Drawing must be done also every frame, because if we didn't draw during a frame, the window will look invisible. So even if we didn't update our game, we still need to draw the things on the screen. And the rest of the code is the same. So let's see what it looks like by compiling and running the game. So we are at 200 FPS here, and the game runs well, and our ft is 4. If we change our frame rate to 60, we are at 16 ft, and our FPS is 60, and we will probably update the game more than once in a single frame. So it runs exactly the same, and precision is not lost. Now let's try the 15 frames example, which broke the earlier calculations. And as you can see, precision is always the same. The game looks choppy, obviously, but we are sure we aren't losing any precision, because we are probably calling update a lot of times per frame with the same ft step variable. So we are just we are just updating the ball and the paddle multiple times per frame. We are not losing precision, and this ensures that the game will run the same on every machine. So this method works quite well, but it has some minor drawbacks. So on a fast machine, the precision of the game logic is less than it could be. Basically, if we set the ft step as 1, our precision will always be 1. Even if the machine is very fast, our precision will always be the same. Usually it's not an issue. On a very slow machine, the number of updates in a single frame can become very big, making the game almost unplayable and delaying the drawing phase. So it's a good idea to limit the number of updates by using a max loops constant. So basically here we could just say if current slice is greater than ft slice and the number of loops is less than max loops, we update. Otherwise we will update the next frame. And with big time slices, object may appear to jump around. That means if we are drawing every frame but updating once every 100 frames, the object will seem to jump around. A possible solution is obviously decreasing the size of the slice, which is the best and easiest solution. Another difficult solution is instead interpolating the object's positions in the drawing phase. So we should separate our shapes in in a separate class, for example, and interpolate the position by the velocity, and it will make the movement look smooth, but it's quite difficult to implement. Also, there are some good resources here to check that talk about the game loop and the frame rate, and especially the second one is very clear and explains the method I just used, so you should check them out. The code now is quite messy, so for the final segment we'll just clean it up a little bit without changing the behavior. Alright, welcome to the last code segment. Now, what we did here is encapsulate our game in a game class, and we will basically avoid having everything inside the main method, and we'll create a game class. This is a very good way of making the code more elegant and easier to maintain. So, as you can see, we have some members that are related to the control of our game, that are the window, the frame time calculations, and a new boolean value that signifies where the game is running or not. And we also have some game entities variables that are the ball, the paddle, and the vector of bricks, as before. So our game construction will initialize the window and create the brick wall. If we had a more serious implementation, it would have been a good idea to have a new game method that could be called at any time to restart the game, and it would basically clear the vector of bricks, reposition the ball, the paddle, and rebuild the brick wall. But for now, we can just simply do all of this in the construction. Then we'll have our run method, which basically is used to start the game and contains the game loop. Instead of breaking out of the game loop, we will use a boolean variable, running, and we will, instead of saying while true, we will say while running. So if inside the game loop we set running to false, we can be sure that we will break out of the loop. It's not a bad idea to organize our code with smaller and smaller methods. In this case, I've divided the game loop in an input phase, an update phase, and a draw phase. It's one of many possible ways of tidying up the code. It's not the best solution in the world, but it works and it's quite elegant in my opinion. The rest of the loop is the same. So our input phase deals with the events and with the keyboard. So we will see here, instead of calling break, we will say running equals false when we press escape. Our update phase deals with the accumulation of frame time inside the slice, and also contains our magical for loop that allows us to maintain our precision at any frame rate. And our draw phase obviously draws all of the objects on the window. So, to start the game, we simply create a temporary variable of type game, like this. And to run it, we simply call .run. Let's see what happens. It behaves exactly as it did before. So, thank you for watching the second episode of Diving into C++ 11. You can fork or look at the full source code for this tutorial and the previous one on my GitHub page, which is github.com/superv1234. Also, check out my website for more tutorials, and to personally get in touch with me, it is vittorioromeo.info. And feel free to contact me at any time. There are links for emails and social networks in my website. So I actually appreciate feedback and comments, and if you have any question, feel free to use the YouTube comments or simply contact me directly. Again, thank you for watching, and stay tuned for the next episode.